Hi, in this video I'm going to go through a tricky question, and it's going to be a complex ion question, and it's from a legacy paper, so January 2012 F325 question 3 should be attached in the information below if you want to have a look. So the question looks like this. We've got cobalt chloride reacting with ammonia, and it forms a range of different complexes. So they contain different amounts of ammonia. Information about these complexes is summarised below. So we've got A, B, C and D. So A has 6 ammonias attached, B has 5 ammonias and then 1 coordinated chlorine and then 2 ionically bonded. C has 4 ammonia and 2 chlorine. D has 4 ammonia and 2 chlorine as well. So we've got some isomerism there going on with C and D. And it just wants us to complete the diagrams below to suggest possible structures for the complex ions A to D. So, if we have a look at this. I'm going to start with A then, which A, just to remind you, had cobalt with 6 ammonias coordinate bonds attached to it, and then it's a 3+ ion, and that forms an ionic bond with 3 chlorides. So the actual complex ion itself, it gives you in the question the octahedral structure for you to draw. And so for A, we are just going to put in 6 ammonias. And it's got it in brackets because it's an ion with a 3+. So that is A. There were 6 ammonias. Now B has 1 chlorine and 5 ammonia. So I'm just going to take one of the ammonias out, put a chlorine in, and now the charge on this, because the chloride, even I said chlorine, haven't I? Chloride is a single negative. The charge now is 2-. So by adding that chloride, cobalt is 3+, chloride single minus, so overall 2-, 2+, 3+, take away a single minus, gives me 2+. Sorry about that. Now in C and D we've got isomers. They've both got 2 chlorines in. So what we're going to look at are cis and trans isomers. So it doesn't matter which way around you do these. I'm going to put the trans as C, and I'm just going to put opposite this chlorine a second chlorine. So now I've added in the 2 chlorines. You could have done cis as C. The charge changes, becomes single plus because we've got 2 chlorides now. So I'm putting for C the trans version, although you don't have to label this. This is the trans version of this particular isomer. And then D then is going to be the cis version. Where if I swap that ammonia around there, this time the chloride is now next to it. So rather than being across the opposite side, it's now adjacent. And so this is cis. And again, single plus. And you could have done that the other way around, but either way, that got you a mark as well. So that's 4 marks. Didn't have to label them as cis and trans, just had to have the 2 different types of drawing, complex ion C and complex ion D. In part 2 then, we've got a bit of an analysis question. And it's worth 3 marks. It's always just worth writing down everything that you know on these. So in the question, we've got chemists provided evidence for the formula of these complexes from their reactions with aqueous silver nitrate. Aqueous silver nitrate reacts with aqueous halide ions in a precipitation reaction. So we've got an excess of silver nitrate solution reacting with 0.01 mole of one of the complexes, A to D, and we form 2.868 grams of precipitate. So with this, we are going to, first of all, write down everything we know. So we've got our complex ion. So this is either A, B, C or D. And on this, we've got 0.01 mole of it. So we'll just put 0.01 to say 0.0 mole. So I'll go to the same number of significant figures plus silver nitrate, and it's told us this is in excess, and that's going to form our precipitate, which will be a silver chloride. Each of the complex ions was made up with chlorides, so when we're at the silver nitrate, we'll get a silver chloride forming, and that'll be our solid precipitate. So we know that the mass of this is 2.868 grams. So you've got to think, well, what can we do here? We don't really know anything more about the complex ion. It could be one of 4 structures. The silver nitrate's in excess, so doing anything with that would be redundant. So we've got to look at this silver chloride. Now, it's given us the mass, and so one thing we could do is work out the MR. And if we know the MR, then we can work out the number of moles. So it's always worth, in these questions, looking, can I work out the number of moles of anything? And if you can, do it, because it's generally worth a mark. So 2.868, if we look at the MR, we've got silver at 107.9 and chlorine at 35.5. So that gives us 143.4 grams per mole for its MR. And so working out the number of moles, I do mass divided by the MR, and that gives me 0.0200. And so that worked out pretty well. The moment I get something as exact as that, I know that's probably what they wanted me to do as well. So what we can see here is that for every one of these, have a look at this, if we look at the ratio of the moles here to here, for every one of these, we're going to get 2 of those, which means in this, we've got a ratio of 1 to 2, but in this structure, we must have 2 chlorines in order for the, or 2 chlorides, in order for there to be twice as many moles over here of the silver chloride. So if we look at the 3 structures and try and have a look, this one's got 3 chlorides, so unlikely. This has got 2, so it's looking like B. This has got a C and D have only got 1. So the one with 2 chlorides is going to be the one that we expect it to be because of this 1 to 2 ratio. So the answer will be B. And that was question 3.